Alrighty, good morning, lads and ladies. Welcome back to College Algebra. Today, we are charging ahead in our new unit, which is so far just been on proportionality. But we're going to start opening that up to studying the functions that kind of show up in the context of proportionality. So it's been a busy morning. I have not had time to unlock your homework yet. Let me go ahead and do that, and then we can get moving here. In the meantime, let's turn this on, get this over here. All right, so the homework set that came due today was homework 9, and that was the direct and indirect or direct and inverse proportionality. And you may have noticed that the class of functions you encountered there were all power functions. That is a function where one variable is described as a power of the other variable, and that is precisely what the next homework set is on. So this will be due next Tuesday, which is the 15th. At 9:30 a.m. of course. And the quiz associated with that will also be due then. Let me say 15. Yeah, 15. Oh. So let's get to it. Another quick reminder, I do still have some people who have not taken the test. I've gone in and begun adding the partial credit to your scores if you have taken the test. I have not gotten to everybody yet, but I will continue working on that. And if you have not taken the test yet, please, please, please remember to come by my office hours on Friday. That is when I'm hosting the makeup session, unless we've made explicit plans to do something else. This is MAC 1105, section 015, which is college algebra. And the date today is the 10th of February 2022. The thing we're discussing today is power functions. And we do have an activity associated with this. We won't do the activity today. We will do it on Tuesday after you've had time to play around with these concepts. But just a heads up, there is another in-class activity coming soon. Okay. So power functions. What are power functions? Well, everywhere in those proportionality problems, you notice, like I said, that one variable was defined as a constant times a power of another variable. Such a relation naturally describes a function. Let me turn my camera back on. So a power function f of x is any function of the form f of x is equal to some constant times x raised to some power. So I'm going to use the function notation throughout, writing f of x instead of y, because I really do want you to start getting a little bit more comfortable with this notation. Remember, this isn't multiplication. This isn't f times x. This is the function's name is f, and the parentheses are like his mouth, and the x is like the thing he's eating. And then this formula tells you what he poops out when he eats the input x. These might seem like they're not terribly exciting at first, but I have a funny story about this. When I was an undergraduate at UF, finishing up my math degree, one of the graduate students I was friends with, who's now a professor there at UF, he's actually at USF now, his name was Joel, has a great YouTube channel. I'll have to try and find that for you later. But he gave me this little differential equation to solve, which was a cute little relationship between one function and its rate of change. where you don't know the function in advance and you're trying to figure it out. And I had taken several classes in differential equations and was pretty confident I would get him something nice within an hour or two. And after a week went by with me working on this in my spare time, I came up to him and said, I have no idea what to do. I'm just like, I'm dead in the water. I've tried Fourier series, I've tried power series, I've tried everything I can think of, and I've got nothing. And he said, well, if you assume that the solution is a power function, then it will fall out right away. And apparently that's what his little brother, who was a physicist, did. He assumed that the solution was a power function, and then very quickly was able to deduce the answer. This is something that physics people do a lot, right? We've noticed in the last homework set, all of those proportionality problems, many of them are application problems, like real world problems, because it is often the case in a real world situation that one object is proportional to at least a power of another object. And assuming that a relationship like that exists is a great way to begin working on a really challenging problem. My goal for us with these functions is severalfold. Mostly, I want to get you a little bit comfortable with the graphs, but then also I want to get you comfortable with the algebra operations involved with exponents. So we looked at some of those basic rules for exponents last time, and I'm going to reiterate those for you today. And then we're going to take a look at the graphs of these things, and then we'll solve, a few of the homework problems that you have to kind of get you ready. So let's begin with some of those rules for exponents. Remember, if I have a product of two numbers raised to a power, I'll number these. If I have a product of two numbers raised to a power, that's the same as raising each of those to that power and multiplying them. If I have a quotient, a fraction, and the whole fraction is being raised to a power, that's the same as raising each to that power and then dividing them. If I have a product with two different powers but the same base, that's the same as that number with those powers added up. If I have a quotient of two powers, each using the same base, then that's the same as subtracting those powers. Put a little divider here. If I take a power like a to the m and I raise it to another power like this notation means you're going to take a and raise it to the nth power, and then take that whole thing and raise it to the nth power. That's a to the m multiplied by itself n times, which would be a times itself m times, all written out n times. So that is n copies of a to the m. That's going to be a to the m times n. And then if you have a power where the power is a ratio, this can be interpreted several different ways. You can think of this as a to the 1 over n all to the m, or a to the m all to the 1 over n. And that's especially useful because this is how roots are defined. So a to the 1 over n, the nth root of some number, I should say, it is the nth root of that number. And then putting this together with number 6, you see that you can write a to the m over n, this object, in either one of these forms, and the 1 over n here would be an nth root. So this is the same as the mth power of the nth root, and this being the same as this because of this. And that is the same as the nth root of the mth power because of this. So these are the rules for exponents that we're going to encounter from time to time in the previous section, in this section, and a lot when we talk about exponential functions. The other thing that is kind of dry, like kind of a little bit of a memory thing, is the basic graph shapes here. So functions like this can look vastly different depending on the power. The power is really what's in charge of the shape of this graph. So I want to build a few graphs here, and we can use our calculator to help us. That will be a nice tool for getting a feel for what these look like. Let's do it. Well, give you just a second to copy these down. Any questions about what's being written here? Anything hard to read? Looking here, I'm not sure this is so clear. It's a minus sign here. We're subtracting. Okay. So we're just going to sketch the graphs of the power functions, the given power functions. And for now, we're going to use our graphing calculator. But the purpose of this example is to introduce and hopefully get you to kind of remember a little bit what these graphs look like. And towards the end of this part, I'll give you a little table with the basic graph shapes for each of these. So let's start with something that we're familiar with, something like one half x squared. This is a power function. The constant c is 1/2, and the power p here is 2. X to the 1/2. Here the constant out front is 3, and the power p is 1/2. And then how about 2x to the -1? Okay. So the first thing I'm going to do here is just annotate with the values of the constant. Here c is 1/2 and p is 2. Here c is 3 and the power p is 1/2. Here c is 2 and the power p is -1. Even though these all have the same basic kind of algebra shape, they're going to have very, very different looking graphs. So let's do it. If you have your graphing calculator, I'll ask you to get it out and play along with me here, because this is something that you're going to want to be able to do on the test. Take a function like this and just sketch its graph quickly using the calculator. Remember to do that. We turn on the calculator, and then we're going to hit this y equals button in the top left. That'll bring up a menu looking like this. You need to be a little bit careful with your parentheses. So when I type 1/2, I'll type that as parentheses 1 divided by 2, and then close the parentheses. So there's 1/2, and I want that to be multiplying x raised to the 2nd power. And we know what shape we should expect here, right? What should be the shape of the graph of this function f? Just checking that we're awake. I see there's something in the chat there. Yeah, this function is a quadratic, right? It's got an x squared and no other wonky powers of x. This is a quadratic, so the shape will be a parabola. Let's take a look, see. So I hit this button over here, graph. And there we have it, right? Nice parabolic curve. So the graph of f. And I'm not going to be super detailed here. f of f is a parabola. Some points on this graph, clearly 0, 0. If you go to x equals 2, then 2 squared is 4. 4 times 1/2 is 2. So this point 2, comma 2 is on there. And then because of the symmetry, the point -2, comma 2 is on here as well. This is the graph y equals f of x. So this graph shape is familiar. The other two are going to be very new. To take a look at the graph of g, I'm going to come over here to y equals again. I'm going to clear out that first entry so I don't have two graphs showing up at once. And then I'm going to type this guy in that same fashion. So here, the constant is just a 3. I don't need any parentheses for that. And then I'll type x raised to the. Now here's where if you're working on the TI-83 or an older calculator, you will need parentheses for this power. So if you have the TI-83 and you're just seeing the little caret symbol here, the little up arrow symbol, instead of actually being moved into the exponent, you'll need to put the 1/2 in parentheses. So I'm going to go ahead and type it like that. So anybody who's following along with a different calculator, which is the right stuff. Always good discipline when you're working with a calculator, put your fractions in parentheses. We'll hit graph. And we see this sort of shape. So root functions often have this sort of shape, at least in quadrant 1. And what this is, for those curious, this is actually a half of a sideways parabola. You can imagine this thing continuing down here. And there's a reason for that. It's related to something called an inverse function, which we will talk about, but not today. Some points on this graph would be 0, 0. And if you plug in 0 for x, the 0 raised to the 1/2 power is 0. And 3 times 0 is 0. If you plug in the number 1, g of 1 would be 3 times 1 raised to the 1/2 power. So 1 raised to the 1/2 power, it's the square root of 1, which is 1. 3 times 1 is 3. So this point would be 1, 3. And then the next number that's going to be nice to plug in here would be the next number that is a perfect square, right? This, again, this 1/2 power is a square root. So I'm going to jump out to 4. If we were to plug 4 in here, g of 4 would be the square root of 4, which is 2 times 3. 2 times 3, that's 6. So this point would be 4, 6. That's the graph y equals g of x. And this last guy is, of these three, my favorite. Because he has some features that we haven't seen on any graph before. This will be the graph y equals h of x. So let's come back to our y equals button here. I'm going to clear this out. And then I'm going to type this guy in, which is 2 times x raised to the, and again, if you're working on the TI-83 or an older calculator, you're going to need to put this power in parentheses. So I'll go ahead and do that. If you're on the 84, you don't have to do it. But just to make it clear what we should do. 2 times x raised to the -1. Okay. Very strange. So let's sketch that shape. Looks like this. This. It might appear to be the case, and some calculators will actually draw a vertical line here. It might appear to be the case that the graph goes up along the y-axis here, but that's not the case. This is an artifact of graphing calculators sometimes. What's going on there is something called an asymptote. And we draw those as dotted lines when we sketch a graph. So there's a vertical asymptote here. And that's just a line that this graph kind of gets closer and closer and closer to as we go further down, gets closer and closer and closer to as we go further up. And there's also a horizontal asymptote here. Some points on this graph, if you plug in some numbers for x, if you plug in 1 for x here, this is 2 times 1 to the negative first power. 1 to the negative 1 is 1 over 1, which is 1. 2 times 1 is 2. So if I mark this as 1, then this would be the point 1, 2. There is a certain symmetry to this graph as well. If this is x equals negative 1, then down here, this point would be negative 1, negative 2. If we come out here on the x-axis to 2, 2 to the negative first power is 1/2. 1/2 times 2 is positive 1. So this would be the point 2, 1. Okay. So here's all three of those graphs. And you see they have very, very different shapes. I want to talk about what dictates the shape of the graph, and then give you some kind of general rules. These are not all the shapes that a power functions graph can have, but if you focus just on quadrant 1, this shape in quadrant 1, this shape in quadrant 1, and this shape in quadrant 1, that actually does encapsulate all the possibilities. G of x here, some functions, some root functions, right, like x to the 1/2 or x to the 1/3 or x to the 1/4, some of those have another piece over here that kind of goes like this, making the thing look kind of like a serpentine. Same is true for power functions. If this power was a 3 instead of a 2, then you would still have a piece over here looking like this, but then instead of the other piece over here going up, it would go down. And with h of x, if this power, this negative power here is odd, right? X to the negative 1, 1 is odd. If that was an even power instead, this branch down here on the left would actually be up here instead. But the quadrant 1 pictures, these are pretty complete. And I want to just explain to you where those quadrant 1 pictures come from, how you can anticipate the shape of the graph in quadrant 1 based on the powers. Okay. So if the power p is bigger than 1, then, and I am assuming that the constant here c is positive, then the quadrant 1 graph shape will look like this, right? Like that parabola. If the power p is between 0 and 1, like 1/2 or 1/3 or 0.1234, then the quadrant 1 shape will be that kind of root function shape that we saw in h of x, that sort of half of a sideways parabola looking thing, something like this. And again, here I'm assuming that c is positive. So here we've got p bigger than 1, p between 0 and 1. The only thing that's missing is p being smaller than 0. And again, I'll assume that the constant c is positive. In quadrant 1, these will all have a shape looking like the 2x to the negative 1 graph over there. Something like this. Those are the basic shapes. I'm writing c is greater than 0 on each of these because if the constant is negative instead of positive, the picture is flipped upside down. Tuck those in here. If p is greater than 1 and c is negative, then it's the same sort of thing, just going down like this instead. just flipped over vertically. If p is between 0 and 1 and c is negative, then you'll have this sort of root function shape, but flipped over vertically, which would look like this. And if p is negative and c is negative, then you'll have the same basic shape you see up there, but again, just flipped over, which would look like this. So these are sort of basic graph shapes for power functions. And I wouldn't recommend memorizing all 6 of these. I would remember these. And then the fact that if the constant is negative, you flip everything over. Flip everything over the x-axis. Let me label the x-axis in each of these. Of course, you have your graphing calculator. So if you are stuck or don't remember this, you can always throw something into your graphing calculator, but knowing these shapes can be very helpful just for thinking about things. For example, if you want to know if the function is increasing or decreasing, knowing something about this shape can be very helpful. It can save you a lot of time. Okay. So what sort of stuff can we do with power functions? Let's take a look at an exercise or two from your homework. Classifying power functions. Well, they want you to indicate rational functions and stuff here too. I guess we need to talk about those. Matching with the graph. This is sort of what we just did. Negative, match with graph, something more fun. No power function. Yeah, even on even. I have something a little bit more engaging here. Yeah. Let's do some of this stuff. This looks like fun. So I will use what we have. All right. I'm going to use slightly different values here. Okay. Yeah, just something like that. Yeah. Okay, and we're going to evaluate the function at the indicated value. So here, let's use something like x equals, anything interesting, integers. Okay. X equals about 32. X equals 1.5. X equals 2/5. X equals can we do that? Oh no, that won't. Okay. Just 4. Okay. So each of these functions is a power function. Some of them have wonky powers, but we can plug these numbers in and see what we get as outputs. And I want to show you as much as we can work by hand a little bit. So at the very least, I want to make sure we're comfortable with the notation. So in part A, I want to evaluate this function k of x at the input x equals 32. That means I'm looking for k of 32. And again, one of the main points of this section is just to get you comfortable with the function notation. So if I want to evaluate this function at the input x equals 32, that means I'm going to replace x here by 32. And we really should write that, k of 32, and then this is equal to 32 raised to the power 3/5. And that 3/5 power is a strange power. But this is actually going to come out really nice. Remember that the 5 downstairs here is a 5th root. And 32 happens to be a perfect 5th power. 32 is 2 to the 5. So when we take the 5th root of 32 and then cube that, we're going to get 2 raised to the 3, or 8. I can show you how to do this in the calculator as well. First, let me describe to you what I just said here. Remember from our rules for exponents, this is the same as the 5th root of 32, all raised to the 3rd power. So you can break this down into pieces if you want to. The 5th root of 32 is actually a nice number. It's 2. 32 is 2 to the 5. So this is 2 cubed, which is 8. Or from the calculator, do it onto that like this. 32 raised to the power, and again, parentheses if you're in an older calculator, 3 divided by 5, close parentheses. And see, we get 8. Let's try the next guy. Now 1.5, that is not a perfect cube. I have no reason to expect this to come out to a nice number, but we can still do the evaluation. H of 1.5 could be 2 times, I'll write this in parentheses here to make clear what's going on, 1.5 raised to the negative 1/3 power. What kind of stuff could we do by hand here? Not a lot, not a lot. I can write this as 2 times 1 over, well, the negative power, remember, sends the whole term downstairs, and then 1/3 is the cube root. So that's 2 times 1 over the cube root of 1.5. But if I was going to enter it into the calculator, I would enter it like this. I think that's actually a little easier than typing this. So here's how we would do that. 2 times parentheses 1.5, close parentheses, raised to them. And again, we've got a weird power here. It's a fraction, it's negative. So I put the power in parentheses as you type, parentheses. And remember, this button down here is the negative. It's not this guy. This is subtract, which is a little bit different. Negative 1 divided by 3, like this. And we get 1.74716, blah, 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 blah. So I'll write approximately equal to 1.747. How about that? No, the 3rd decimal place. Any questions about how we were inputting these in the calculator or the work that we did by hand here? Okay. Moving on, we want to evaluate this function, x to the 0.123 at the input 3/5. So that would be f of 3/5. This is the output we get from the function f when we plug in 3/5 for x. And again, I'll use some parentheses here because I want to make clear that everything is being raised to this power. This is 3/5 to the 0.123. And again, following our rules for exponents, if we wanted to, we could write this as 3 raised to the 0.123 divided by 5 raised to the 0.123. And those are equivalent. And you could enter it into your calculator either way, like this or like this. But there is no nice way to evaluate by hand 3 to the 0.123 or 5 to the 0.123. it's not a nice power, and this is not a perfect power of any number. So I will enter it the first way in the calculator. That's parentheses 3 divided by 5, close parentheses, raised to the power of 0.123. And for our output, we get something like this, 0.939101. I'll round up the third decimal place again. So this is approximately 0.939. This last guy, the exponent is negative, and it's also a slightly weird decimal. And we're going to evaluate this at x equals 4. The reason I had to get rid of the negative there is because you cannot raise a negative number to a wonky root power. So if you try to raise a negative number, let's just really quick see what happens. If I take parentheses -4, and I try to raise it to, even forget about the fact that the power is negative, just 1.34, I'm going to get an error. Right? Because if you take a negative number, remember a fraction in the power is the same as a root, like we saw up here. This was a fifth root. If you raise a negative number to a weird fraction power, then there's a chance that your output will not be a real number, like trying to take a square root of a negative. So here, what we want to do, we want to evaluate this function at 4. That means we're looking for g of 4. And that would be 4 raised to the negative 1.34 power. So we don't need parentheses for that. I'll just type 4 raised to the, and then here again on the older calculator, we'll want parentheses negative 1.34. Close the parentheses in the power and hit enter. And we get 0.156 blah, blah, blah. Okay. So evaluating these functions, not terribly hard. You just need to be careful with your parentheses and mindful of your order of operations. Before I move on from this, are there any questions about what we did here in purple, how we came up with these answers, or any of the work we did by hand?
For C, do you have to break it down to the fraction form to get?
Nope, either one is fine. Actually, to get this number, I entered it in the calculator in this way. But
Okay.
you could do it either way. So
I must have just did something wrong because it just didn't come out like that.
So it's probably a calculator thing, right? Like a parentheses thing. Let me show you both ways. So here's 3/5 raised to the 0.123. That's giving me this 0.939. And then if I separately take 3 raised to the 0.123, then you need to make sure you get out of this power before you divide. So remember, if you're using an older calculator, put the power in parentheses and come down out of the power, close that parentheses, or on the 84 or newer, just hit the right arrow button to get down out of the parentheses. Then we can divide by 5 raised to the 0.123. We get that same thing. So either way is okay, but we do have to be very careful with what we tell the calculator. The calculator is not an intelligent being at all. It just follows the PEMDAS rules blindly. So lots of parens.
Thank you. I put the wrong thing in parentheses.
Okay, yeah, no worries. And this is something you should experiment with, right? That's the purpose of this sort of problem. It's not so much that there's anything super enlightening about plugging numbers into a function, but getting comfortable with the parentheses in the calculator is one of those things, because it's so sad and so frustrating to get a question wrong on a test because you just put the paren in the wrong place in the calculator. So do really practice these. And as you practice them, use the calculator you're going to use on the tests. Okay. I would like to take a quick look at each of these graphs because we're here, and one of the big things is getting to know these graph shapes. Maybe not all of them, but now let's go ahead and look at all of them. So hit y equals, I'll clear out what I have here. We don't need to draw anything, we're just going to do this, but play along with me. So I'm going to type for that first function x raised to the parentheses 3 divided by 5, close parentheses. So this is the function k of x at the top, and I'll hit graph. kind of nifty looking. Now, if you look just in quadrant 1, you notice this does have that increasing sort of concave down shape of the root functions that we said it would have. Right? This guy has this basic shape in quadrant 1, but he's different than the root function we graphed here, which only has the quadrant 1 shape. This guy has that serpentine thing going on that I talked about, and that's because he's an odd root. It's the 5th root. If that was a 4th root, like 3/4 power, you would see a shape that looked exactly like the one we did on the previous page, just having this piece here. But if the downstairs power is odd, then you'll have this whole serpentine or S-shaped thing. Let's take a look at the graph of this guy. What do we expect here? Based on the power and the constant, what sort of graph shape, which one of these graph shapes do I expect to see? Let's say the first one, the second one, or the third one.
The third?
Yeah, exactly. So here the power is -1/3. -1/3 is less than 0, right? Less than 0 just means negative, greater than 0 just means positive. So because the power here is less than 0, I expect, at least in quadrant 1, the graph to have approximately this shape. Let's see what we get. 2 times x raised to the power of, parentheses, -1/3. Oop, I typed 13, not 1/3. So that would have been divided by 3. There we go. Now close bracket. All right. Hitting graph. There's something going on over here now. And this looks a little bit weird, doesn't it? It looks like this graph just boop hits the y-axis. But I claim that it does not, that it really is this thing. And this is another one of those subtle things. It's possible to get these graphing questions a little bit wrong if you don't remember the stuff that we show here. That's why we teach graphing by hand as well as the calculator. What's going on here is that this graph is just so close to the y-axis and the resolution of the screen is so low, right? You can actually see the individual pixels here that we're not able to tell. The calculator can't show us at this zoom level where the graph is different from that y-axis. Now, if I change my window settings, let's go -2 to 2 for the x value. So we're kind of zooming in horizontally. That's okay, Lena. So what we did is we just used the calculator to sketch this graph. And what we saw is that it instead of looking exactly like this, it looked like this thing just ran into the y-axis and stopped. And I claim that that's wrong, but in order to see it, we need to zoom in a little bit because the resolution of the calculator screen is so poor. So here I am zoomed in, just looking at x values between -2 and 2. And you can see a little better if we go just -1 to 1. You'll see a little better still. You see we're getting more and more of this curve here. But this is just the limitation of the TI-84, and it's kind of disappointing. To really verify this, we can use a more powerful graphing utility. So we call it h of x equals 2x to the -1/3. There we go. See? So what's going on there is that the TI-83, TI-84, the resolution on the screen is so low that it looks like this thing is actually hitting the y-axis on the TI-83, 84. But if you use a more powerful graphing utility, you'll see that this graph does not actually hit the y-axis. There's a little bit of distance there. And we do indeed have that shape, right? We have this kind of hyperbolic shape. You can compare the output from the graphing calculator, which makes it look like this thing has a y-intercept, to the output from Desmos, where you can see that it really does not have a y-intercept. And that's one of the features of these power functions. If the power is negative, then there is no y-intercept. That graph will never actually hit the y-axis. Why is that? Think about the domain rules we talked about, the domain red flags. If I apply my rules for exponents here, I see this is 2 times 1 over x to the positive 1/3. Right? The negative power brings it downstairs. And that's the same as 2 times 1 over the cube root of x. So there's a variable downstairs in this fraction. And if you were to plug in 0 for x, you'd be dividing by 0. Now remember how we find y-intercepts. Y-intercepts you can always find by plugging in 0 for x. Well, 0 is not in the domain here. So this function and any power function where the power is negative, none of those will have y-intercepts. They all have those asymptotes at x equals 0. Okay, let's take a quick look at the last 2 graphs. This guy, that power 0.123, that's the same as 123 over 1000. That's a fraction in the power. And that fraction is smaller than 1, so I expect the root shape here. X raised to the 0.123 graph. Oh, we need to change our window settings. Let's go back to the standard window settings. 10 to 10. Let me try. There we go. Now this time it's zoomed in too far, zoomed out too far along the y-axis. So if I want to get a better picture for that graph, maybe I'll change my y settings from -10 to 10 to something like -2 to 2. There we go. And there's that root shape. This shape. And again, it looks like there's a y-intercept here, but really it's down at the origin. And that's again just the limitations of the graphing calculator. That resolution is poor. This graph comes in, gets very close to the y-axis, but doesn't touch the y-axis until we get down here. But because the pixels are only so wide, we're very limited in what that can show. What do we call this? F of x. So I type x and then shift 6 to get into the power, 0.123. And so now come down. There it is. Right, and we do see that root shape. This shape. It's just very exaggerated in here. Okay, last one. X to the -1.34. Which one of those shapes do we expect from this guy? Shape 1, shape 2, or shape 3?
Three.
Very good. We expect the third shape again, because here the power is negative, just like in the one before. So I type x raised to the parentheses -1.34. There it is. Very nice, right? Again, I don't have anything in this quadrant because that will only show up if you have an odd integer, and it would be up here if we had an even integer. All right. The next thing I want to talk about is not necessarily a power function thing, but it is a classification thing because this shows up in this new homework set. We're going to define some objects. So you notice in those first few problems, they're not just asking about power functions, they're asking you to classify as a power function, a polynomial function, or a rational function. So first, let's talk about what polynomial functions are. We're going to study these in detail later. But this is what you get when you combine, so adding and subtracting power functions where the powers are positive whole numbers. All right, so for example, every quadratic is a polynomial, like 3x squared minus 2x plus 5. That's a polynomial because each one of these pieces is a power function. 5 here, secretly the power is just x to the 0 multiplied by a constant. You could have a larger order polynomial, something like x to the 7 minus 3x to the 4 plus x squared minus 2. Again, positive whole number powers of x together with constants. And then a rational function, we will also study these in detail. These are fractions made up of polynomials. And these can be a little bit sneaky. Something like 1 over x is a rational function. The top here is a constant, but that is technically a polynomial. And the bottom here is x to the 1, which is technically a polynomial. Or you can have something like 2x plus 3 over x minus 5. Again, whole number powers of x, positive whole number powers of x, together with constants. And then you just take two of those things and form a fraction out of them. And you can have more complicated stuff like x to the 4 minus 16 over x to the 5 plus 32. Anything like that, say fraction where the top and bottom are polynomials would be a rational function. And each of those are families of functions that we're going to study in great detail down the road. Okay. The last topic that I kind of want to introduce to you here today, the last kind of new concept is a fairly deep one. And it's something that's going to persist as we study polynomials and rational functions and other things. This is the concept of parity, P-A-R-I-T-Y, parity, which means even and oddness. So when we talk about whole numbers like 2, 3, 4, 5, 6, we can categorize them as being even if they're divisible by 2, or odd if they're not divisible by 2. It turns out that mathematicians like to study functions, and if you think about collections of functions, a lot of them have some properties that are kind of similar to numbers. In fact, polynomials are usually by mathematicians considered to be like the function version of whole numbers, because a lot of algebra properties that whole numbers have, polynomials have. For example, when you add two whole numbers, you always get another whole number. You add two polynomials, you always get another polynomial. Multiply two whole numbers, you always get another whole number. Multiply two polynomials, you'll always get another polynomial. And just like numbers, whole numbers can be classified as even or odd. Functions can be classified as even or odd. However, not all functions live in one of those categories. That it's also possible for a function to be neither even nor odd. So this is a definition. The function f of x is called even if, and there's kind of two ways to think about this. One of them is an algebra thing, just a purely algebra or analytic thing. And the other one is a geometry thing. So the algebra definition here is that f of negative x is the same as f of positive x. So what I mean there is if you plug in the negative version of some number, the output will be the same as if you plugged in the positive version of that number. And as a consequence of this, there is a geometric fact that even functions, their graphs have a certain symmetry. So here, for example, is the graph of f of x equals x to the 4. It's kind of like a parabola, but it's sitting down on its butt. It's been like flattened out. The property of the graph that tells you this function is even is the y-axis symmetry. I'll show you another example here. This is the graph of f of x equals x to the 2/3. That's a power function, and in quadrant 1, it has that root shape. But this is also an even function. It has that symmetry, that y-axis symmetry. Another power function that lives in this family of even functions this is f of x equals 1 over x squared. And what we see is that all these graphs are symmetric about the y-axis. If you were to fold this graph over the y-axis, it sits right on top of itself. If you fold this over the y-axis, it sits right on top of itself. If you fold this over the y-axis, it sits right on top of itself. Graphs of even functions all have y-axis symmetry. And for each of these, I can show you that this thing is true. All right, so let me show you over here the algebra thing that corresponds to this geometry thing, the symmetry. F of x equals x to the 4 is even because, you could say because the graph has y-axis symmetry, or if you wanted to use this definition, we can look at what f of negative x is. And this is again where that function notation is very important. F of negative x, this means instead of plugging regular old x in here, I'm going to, in parentheses, plug negative x in there. So this is negative x to the 4. And if I want to show that this function is even, I need to show that this is actually the same as this. And here's one way to do that. Negative x is -1 times x. So what I'm doing is raising all of that to the 4. And then from our very first property of exponents, this is the same as -1 to the 4 times x to the 4. And when you write a negative raised to a power, again, very important, you put it in parentheses. It means different things without the parentheses. -1 to the 4 is -1 times -1 times -1 times -1. It's 4 copies of -1 multiplied by itself. -1 times -1 is +1. So this is +1 times +1, which is just 1. That's just x to the 4. Well, what is x to the 4? That's the original function. So what we've just done here is proving that the function f of x equals x to the 4 is even, because we're able to show that f of negative x is equal to f of positive x. Pretty cool stuff, right? This type of thing, by the way, this is what's called a proof, is what mathematicians do. Now, a lot of people have the impression that mathematicians sit around like just doing calculations all day. And that's not the case. What we do is we like to prove things. So we come up with a question: is this true? Is this function even? Is this function odd? And then we try to prove, yes, it is, or no, it isn't. So this would amount to a proof that f of x equals x to the 4 is an even function. Questions about what makes an even function even? I have a question for you. In terms of the definition of each of these functions, like x to the 4, x to the 2/3, 1 over x to the 2, do you notice anything about the definitions of those functions that kind of makes you think of the word even? Think about these powers. 4, 2, 2, they're all even powers. If you have a power function where the powers are all even, then you automatically have an even function, and that's kind of a cheat code. Let me show you a few at once. X squared is even. X to the 4, that's the one we just looked at, is even, right? It kind of looks like a parabola, but it's got this, like, its butt has been smashed down on the ground. X to the 6 will be an even function. X to the 8. X to the 8th power will be an even function. So these all have that same sort of symmetry. And what you notice is that as the power gets bigger, the butt gets flatter, right? This thing gets smashed into the x-axis more. So when you're talking about even powered power functions, they all have this kind of shape. And as the power gets larger, the bottom end gets flatter. That's all that happens. Now, if there's such a thing as an even function, there is bound to be such a thing as an odd function. And it will have a algebra definition and a geometric interpretation, some sort of symmetry, just a different symmetry. So things I need you to remember from this: graphs of even functions all have y-axis symmetry. And the definition of an even function is this. Okay. And there's that little cheat code that if you're looking at a power function where the power is an even number, that will be an even function. It's a nice little cheat. Now the function f of x is called odd if f of negative x is equal to negative f of x. This is what we mean by an odd function. And just like with even functions, there's a way to describe this in terms of a symmetry. The graph of x cubed. We know, because this is a power function with a positive constant and a power bigger than 1, that in quadrant 1, its graph will look like this. And this particular guy on the left side will look like that. Kind of like the cube root or the fifth root function, just turned upright rather than sideways. The cube root and fifth root functions are also examples of odd functions. I'll write that in the power function form, like x to the 1/3. This, because it is a root function, it has a power that is between 0 and 1, and quadrant 1 will have this shape. Over here, we'll have a shape like this, that serpentine type shape. And you see, these are actually very similar functions. The exact relationship between these, this guy is the inverse of this guy, in a sense that we'll talk about later. And then a kind of type 3 graph shape here that would count as an odd function. 1 over x, or x to the -1. That's a power function with a negative power. This is x to the -1. So in quadrant 1, we expect that shape. And we have a corresponding piece over here. I want to emphasize again that these do not hit the y-axis. All right, if you're asked to draw a graph of a function like this, please don't show it hitting the y-axis. They don't do that. These are odd functions, and their graphs they will always have. The type of symmetry here is a little bit harder to describe. If I take a point on this graph, it's not y-axis symmetry, right? I can't fold this over the y-axis and land back on the graph. But what I could do is fold it over the y-axis and then over the x-axis. That will get me back here. And that is equivalent to reflecting through the origin. And for that reason, we call this symmetry origin symmetry. If you take a point on the graph of any odd function and reflect it through the origin, you will land back on that graph. So these graphs always have what we call origin symmetry. I always say they're symmetric about the origin. And like we did with that last guy, I want to take one of these and prove that he is an odd function using this algebra definition here. Just to make sure we're comfortable with both definitions, both ways of thinking. Let's go ahead and, no, these will all be fun. I'll let you guys choose. Tell me in the chat or just shout out which one of these guys would you like to do? X cubed, x to the 1/3, or 1 over x?
The second one.
Okay, so let's prove or show that f of x equal x to the 1/3 is an odd function. So again, what we want to show here is that f of negative x is the same as negative f of x. Even functions gobble up negative signs. Odd functions spit them out. So if you feed an odd function a negative, he's going to spit it out. And the even function just eats it up and it goes away. All right. So we need to begin by looking at f of negative x. And we want to show that that's equal to negative f of x. Well, f of negative x is parentheses negative x raised to the 1/3 power, because f of x is x to the 1/3. I'm going to write this as a root. This is the cube root of negative x. Right? Remember that rule for exponents. A to the 1 over n is the nth root of a. And just like we did in the last one, negative x I will write as negative 1 times x. So this is the cube root of negative 1 times x. Right? Negative 3 is negative 1 times 3. Negative pi is negative 1 times pi. Negative x is negative 1 times x. Now I've got two numbers, both under this root, and they're being multiplied. Or if you like, you can think of it as applying that first rule from our rules for exponents. So if you have two numbers multiplied all raised to some power, like this is all raised to the 1/3 power, you can give that to them separately. This is the cube root of negative 1 times the cube root of x. And then we need to think about the cube root of negative 1 a little bit. You know that when you take square roots of negative numbers, we get into trouble, right? Like the square root of negative 1 is I. It's a complex number. What about the cube root? What is the cube root of negative 1 and why?
Okay, so don't quote me on this, but I think it's 1 because it's uneven, it's odd.
You're right in a sense. So because this is an odd root, what we will get here is a real number. We're not going to get a complex number out, and that's good news. But it's not going to be 1. So let's see. We have an nth root button in here somewhere. Here it is. You hit math and scroll down. You see there's a dedicated cube root too. So I can go down to the cube root and enter in here -1 and see what it gives me. -1. Why is that? That's a little aside. Yeah, this is correct. So the cube root of -1 is equal to -1. Remember what an nth root means. It means the nth root of some number is another number such that when you raise that second number to the nth power, you get the original. This is because -1 cubed is equal to -1. Right? And the general rule there is that the nth root of a is equal to b means that a is equal to b to the n. That's the definition of a root. So the cube root of -1, this piece right here, is going to be -1, because if you cube -1, you do get -1 back. So this piece is -1 times this piece is still the cube root of x. And that's negative x to the 1/3, right? Cube root of x is x to the 1/3. And then we compare this to the original function. Is this the original function? No. But is it the negative of the original function? Yes. And that's what we wanted to show. Remember, our goal here was to show that f of -x is equal to -f of x. That is the definition of an odd function. Okay. So these are power functions. These are power functions, and they're powerful, pardon the pun, powerful functions. You can do an awful lot with them. And if you're looking in physics or other places, you'll be surprised how often the relationship between one important object and another, like the force due to gravity, and the distance between two objects, that's a power function. So many things like that. Momentum and velocity, power function. Kinetic energy and velocity is a power function. The last thing I want to do is show you some more examples of these things in Desmos. We did that for even functions, so I feel like we should do it for odd functions. So x cubed, here he is. x to the 5th, x to the 7th, x to the 9. One that I haven't listed here is just y equals x. This is also an odd function. He has that origin symmetry as well. But he doesn't have that graph shape, so I'll exclude him from this. And you see the same sort of patterns that we noticed before, right? If you start with kind of the prototypical odd function, x cubed, and you want to look at larger powers that are also odd functions, it's going to have the same basic shape, but it's going to get more and more flat near the origin. So comparing x cubed to x to the 5, same basic shape, but x to the 5 is a little bit flatter near the origin. And as the power goes up, they just get flatter and flatter. So until you get down to something like x to the 9, which looks like it's glued to the x-axis between -1 and 1 almost, and then turns up. But it's still that same basic shape. Okay. You may notice a pattern, right? Just like if you have a power function where the power is an even integer, that will be an even function. If you have a power function where the power is an odd integer, that will be an odd function. Now, these are not the only types of even and odd functions, right? Here, this power is not even an integer, it's a fraction, it's 1/3. Here, this power is negative, and you still have an odd function. So in that same way, you can construct lots of other guys, like 1 over x cubed will be an odd function. That's x to the -3. And any odd root like x to the 1/5, x to the 1/7, x to the 1/9, those will all have this basic shape as well. So the main thing in this section is the graph shapes, right? And we want to get those in your head nice and clear. I do have a Desmos environment with a bunch of graphs in here that I tell my calculus students they need to know all of these. This is 1140 somewhere. I'll just open this one for now. So in here I have a bunch of different graphs you can just pull up really quick if you need to look at them. You're welcome to do that. I can give you this. This is not something that I require you to memorize or anything, but it is, I think, sometimes a useful tool. So graphs. There are trig functions and other things like that in here because these are for like calculus students. There are exponential functions, I think maybe. Oh no. So let me get rid of these because if there's 1140 primarily need it. I'm gonna update that link here. Here we go. All right. So that is all I have for you guys today. Is there anything you'd like to ask me before we wrap up?
Yeah, I wanted to know, how do I read the grade book? Like, all I see are percentages, but not an actual grade.
Let's see. I don't think I can pull up the grade book without showing everybody's grades. Give me 1 second to fiddle around here and see if I can find a way to do that for like a test student or something. Yeah, so when I log in as a test student, I get this invalid student ID thing when I go to the grade book. But you should see probably percentages in each category, right?
Right, so I have to calculate my grade?
If you're not able to view the total grade in there, so unfortunately I'm not sure because when I go to the grade book in the student view, I don't see anything, but worst case scenario, yes, you can calculate your grade from those percentages using the information in the syllabus. So each category has a certain weight. If you come to the syllabus here, you see participation is worth 5%. Online assignments, that's the homework and quizzes in my open math worth 10%. Activities and projects are 10%. Midterm exams are 50% overall, or 12.5% each. And then the final exam is 25%. So you can use these weights together with the percentages in my open math to calculate them. Like if you have all your class participation points, you haven't lost anything there. You're doing all the homework and stuff. Maybe you did one of the 2 activities and you did the project, then you can calculate by taking each of those percentages in that category and multiply online participation, 100% in that category times 0.5 or 0.05, whatever your percentage is in the online assignment, multiply that by 0.1 and do that for each of these categories, then add them up. That will be your total grade.
Okay. Thank
But I'll
you.
see, if you can come by office hours, we can do a screen share thing and I can try to navigate you to a place where you can just view your total grade without having to do that. I just don't want to show everybody's grades all at once.
All right, awesome. Thank you.
Yeah, of course. Alrighty, guys, unless there's anything else you would like to ask, we're gonna go ahead and wrap up here. Is there anything else you need from me at the moment?
One more thing, I just wanted to remind you about that quiz review that I emailed you about.
Quiz review. Let me see. Remind me what the issue was there?
It was the question answer was wrong, so I got it wrong,
Oh, yes.
even though I had it right.
Thank you. Thank you. Yes, yes, yes. This is something I wanted to mention to everybody because this one of the questions in the test one quiz review had an improper key. It was when you were solving like k of x equals 7 from the table. That's an
The
issue.
same thing happened to me.
Yeah, I think it happened to everybody. If there was an issue in the key in the master course, then that would have gone out to everybody. So I emailed the course coordinator and I asked her if she wants to make the change in the master course so it trickles down automatically, or if she wants me to go in and do it myself. So I will fix that. I think probably everybody ran into that issue because it was a problem with the key in the master course. I apologize for that. I know that's so frustrating, but I will make sure you get the credit for that question, and hopefully we won't run into any more of those things.
Thanks.
Of course. Thank you for reminding me. All right, guys, I'm going to go ahead and wrap it up here. I hope you all have a lovely rest of your day. I do have an office hour starting at 11 if you need to come talk to me about anything. Otherwise, just make sure you're keeping up with that homework in my open math, and I'll see you on Tuesday. Remember, activity on Tuesday.